Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 41, first missing positive. This is a medium difficulty problem, often popping up in coding interviews, so it's a great one to master. The problem statement is pretty straightforward. Given an unsorted integer array nums, find the smallest missing positive integer. For example, if we have the array 1, 2, 0, the smallest missing positive integer is 3. If we have 3, 4, negative 1, 1, the answer is 2. Notice that we're only interested in positive integers, and the answer might be greater than the length of the array. The constraints are that the array length will be less than or equal to 500,000, and each element will be within the range of negative 2 to the power of 31 to positive 2 to the power of 31 minus 1. So, how can we efficiently find this missing positive integer? Let's dive in. Understanding with examples. Let's solidify our understanding with some more examples. Consider the array 7, 8, 9, 11, 12. The smallest missing positive integer is 1, right? Now, let's look at 1, 2, 3, 4, 5. Here, the smallest missing positive integer is 6. See the pattern? It's not just about looking for the next consecutive number, it's about the smallest positive integer missing from the sequence. Let's take another example. 1, 3, 4, negative 1, 1. Here, we ignore the negative number, and 1 is already present, so the answer is 2. These examples highlight that we need an algorithm robust enough to handle various scenarios, including arrays with negative numbers, duplicates, and gaps in the positive integer sequence. This is where clever algorithmic thinking comes into play. Let's explore some approaches to solve this. Brute force approach. A brute force approach would be to sort the array, iterate through it, and check for the smallest missing positive integer. We could then create a set of positive integers from 1 upwards and check for missing ones. This is simple to understand, but incredibly inefficient. Imagine a large array. Sorting it takes O of n log n time, and then our linear search is an additional O of n. So our total time complexity becomes O of n log n, which isn't ideal for large inputs. And the space complexity will at least be O(n) to handle the sorted array and the set we created. We need a much more efficient approach. Let's think smarter, not harder. Optimal solution. The optimal solution cleverly uses the array itself as a hash table. We can utilize the array indices to represent the positive integers. For each positive number in the array, we can try to place it in the correct index. This means if we see a 1, we put it at index 0. If we see a 2, we put it at index 1, and so on. We'll only consider numbers within the range of 1 to n, where n is the length of the array. Because of the constraints provided at the beginning of this problem, we can be certain that the solution is less than or equal to n plus 1. After this manipulation, we simply iterate and look for the first index where the element is not the expected one. This gives us the smallest missing positive integer directly. The intuition behind this algorithm is quite brilliant. It allows us to solve the problem in linear time and constant space. Code implementation. Let's see the code in Python. We'll first handle edge cases where the array is empty. Then we'll iterate through the array, adjusting the placement of the numbers as discussed. Finally, we iterate to find the first index which does not match the expected value. Here's the code. This Python code implements our optimal algorithm efficiently and concisely. Time and space complexity. Now, let's analyze the time and space complexity. The algorithm consists of 3 main loops, each iterating through the array once, making the time complexity O of n. We're not using any additional data structures that grow with the input size, we're using the array itself for our hash table. Therefore, the space complexity is O of 1, which is constant. This is a significant improvement over the brute force approach, making our solution efficient for large data sets. This constant space is a huge win for memory optimization. Engagement break. Before we wrap up, I want to encourage you to like this video if you found it helpful, subscribe to the channel for more LeetCode solutions, and leave a comment below with your approach to this problem or questions you might have. Did you solve it using a different method? Let's discuss. Sharing your thought process is a great way to learn and helps build a community of learners. Conclusion. In this video, we conquered the first missing positive problem on LeetCode. We started with an understanding of the problem, explored a brute force approach, and then delved into an optimal solution that cleverly uses the input array. This optimal approach has a time complexity of O of n and a space complexity of O of 1. Remember, understanding the underlying principles of algorithms and data structures is key to acing coding interviews. This problem is a great example of how optimization can drastically improve the efficiency of your code. Make sure to practice this problem and similar ones to hone your problem-solving skills. Don't forget to like this video, subscribe to the channel for more algorithm tutorials, and share this video with your fellow coders. Until next time, happy coding!